Hello students, welcome back to the class. So we will continue with the chapter structure of atom. So today will be the part 7 of it, the last part. Disclaimer, the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creator and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. In this lecture, we will be seeing the above principle, the Pauli exclusion principle, and the Hund's rule of maximum multiplicity. Second thing is that we will be focusing on the writing of electronic configuration for different type of atoms. So our subtopic would be first is the energies of orbitals. So before studying all these rules of filling the electron, we will try to compare the orbitals energy with each other. Okay. So second thing, we will see the filling of orbitals in the atom. Third is the electronic configuration of the atoms. So moving on to the first topic, which is energies of orbital. So there are two types of atom in which you will compare the energies. First is the hydrogen-like species. Now what is the meaning of hydrogen-like species? So every species which has one electron is considered to be hydrogen-like species. So you can take hydrogen first of all, which is having one electron itself. Then if you take helium plus, so we are not taking the neutral helium, we are extracting one electron from it, and then we are taking the positively charged helium plus ion. So of course, if one electron is removed, helium will also have one electron. Similarly, lithium, beryllium, all of this, if we remove the necessary amount of electron and keep the electron as 1, then the species that will be formed will be called as the hydrogen-like species. Now, in this type of species, the energy distribution looks like this. So if I take the first shell, so first shell has 1s. If I take the second shell, then it has 2s and 2p. Now both of the orbitals will have the same energy. What about the 3s, 3p and 3d? So similarly, they all have the same energy. And lastly, 4s, 4p, 4d and 4f have the same energy. So the energy is only changing when we are changing the shell number from 1 to 2, 2 to 3, 3 to 4. Now, very important point, remember this, that this is only true for hydrogen-like species and not for other species which has multi-electron. Means it has more than one electron. Now, although this 2s and 2p have different shape, we know it, S has a spherical shape and P has a dumbbell shape, but still they have the same energy. And these type of orbitals which have the same energy are named as the degenerate orbitals. Okay, so they are called as the degenerate orbitals. Next thing, so if you take an hydrogen atom and we are taking its electron in the most lower state, so the most lowest state will be n is equals to 1. In that case, it will be called that the hydrogen atom is in the ground state. Next thing, if your electron is not in the ground in the lowest state, in addition to that, it is in the 2s, 2p or higher orbitals like 3s, 3p or 3d. In that case, your hydrogen atom will be in the excited state. So we have already seen this in the atomic spectra. Then when that what happens when we increase the energy of the hydrogen molecule. I guess this part is clear. Any doubt? So anyone has any doubt in this part? Remember, all of this are applicable only to hydrogen-like species and hydrogen. Now questions are asked from here in the competitive exam because the normal idea of the energy is quite different. So let us see it for the multi-electron system. Means, so I guess I have explained a lot about this hydrogen-like species from the starting only. So all of the species that have one electron are named as hydrogen-like species. So if you take a helium, so Laksh, how many electrons does lithium have? I'm asking about lithium. Okay. So I'm talking about lithium. So hydrogen, helium, lithium. So if you remove two electrons, how many electrons will be left? If I am removing two electrons from it, how many electrons will be left? One electron. Yes, Laksh. So in that case, it is behaving like a hydrogen atom because hydrogen atom is also one electron. Therefore, lithium 2 plus, since we have removed two electrons, so there will be two positive charge. So lithium 2 plus will be a hydrogen like species. Is it clear now? Okay. Now we will move to multi-electron system which has more than one electron. In this case, the energy order looks like this. Now, how are we deciding that which one is in a lower energy and which one is in a higher energy? We'll talk about it later. But the major thing to notice here is that it is very different from the hydrogen-like species energy distribution. There we have 2s and 2p having the same energy, okay? But here 2s is having a lower energy than the 2p. Now how this energy order is decided, again we will see it in the coming slide, but first we have to see that why the difference is coming for the case of multi-electron system and why hydrogen-like species have a different electronic energy distribution as compared to the multi-electron system. So in case of hydrogen-like species, the energy was only dependent upon the n values. If you change the n value, then and then only the energy was changing. But here, in the multi-electron system, the energy is dependent upon both the value of n, which is the principal quantum number, and L, which is the azimuthal quantum number. Okay. So if you see here, then you can see very clearly that the P has a different azimuthal quantum number and S has a different azimuthal quantum number. So for S it is 0, for P it is 1, and therefore its energy is changing. Right? So in the case of multi-electron system, remember that the value of energy will not only depend on the value of principal quantum number, but also on the azimuthal quantum number on the subshell notation. So if I talk about the energy of orbital in a given shell, okay, suppose you have a given shell, your shell is not changing, but your orbital is changing. Suppose you are comparing 3s, 3p and 3d in a multi-electron system. So listen it very carefully. If you are comparing the 3s, 3p and 3d, that means you are not changing the value of principal quantum number, which is 3, but you are changing the value of azimuthal quantum number, which is 1, 0 and 2. For S it is 0, P it is 1 and D it is 2. So you will see that the 3s will have the lowest energy, then comes the 3p, then comes the 3d. Okay. So this is important point to remember. What? Again I am repeating it. If you are changing the subshell, then you are increasing energy as S, P, D and F. So for a given shell, the value of L is important. Now, why it is happening? Why there is a difference between these two? So the reason behind this disparity is that in case of a hydrogen-like species, we have only one type of force that was present within an atom, which was electron and proton, electrostatic force between electron and proton. But here, in multi-electron system, we have a second force, which is repulsion between the electron and other electrons present in that atom. And due to this new repulsive force, we are seeing a change in the energy distribution. Okay. Now let us try to understand that how this new repulsive force is changing the energy order. So we can describe the same with the energy level diagram. So the A here is for the hydrogen. So you can see 1s is in the lowest energy, then 2s and 2p are in the same energy, then 3s, 3p, 3d are in the same energy. Whereas in the case of multi-electron system, which has more than one electron, 1s is in the lowest, then 2s, then 2p, then 3s, then 3p, 4s, 3d, and so on. So there is surely a change in the energy distribution. Okay. And one thing is very important. If you look for the 3s, 3p, and 3d, then I have told you earlier that the S will have the lowest energy. So 3s is in the lowest, then 3p, then 3d. But there is a 4s in between. We will talk about it, how to decide this order. But the point here I am trying to make is that the energy order will change, and for the same principal quantum number, the value of energy will change for different type of subshell. So 3s has the lowest energy, then 3p, and then 3d. Now, how we will decide that which one will have a lower energy and which one will have a higher energy? So it's very simple to understand that. First thing you have to do is you have to calculate the n plus L value for a given subshell. Now, the orbital which has a greater n plus L value will have a greater energy, and the n plus L value is the deciding factor. Now, if the n plus L value is same for two different subshell, then in that case, the subshell which has a greater n value will have a higher energy. So let us try to understand this. So first of all, let us try the 1s orbital. Okay. So 1s orbital, the value of n is 1 and the value of L is 0. Therefore, n plus L value is 1. For 2s, it is 2. So 1s will have the lowest energy because its n plus L value is less, and 2s will have the higher energy because its n plus L value is higher. Now, if you see 2p and 3s, then they both have the same n plus L energy. Then the question arises, which one will have a lower energy? For that, now you have to look upon the n value. So since 2p has a lower n value, therefore it will be lower in energy. So remember, if two orbitals have the same say value of n plus L, then you have to look for the n value. Now moving on to the next, again we have 3p. So we know it very well. It will be 4. So n plus L value is higher in this case. Now coming on to 4s, it has a same n plus n value. Now how we will decide between 3p and 4s? Again we will look at the n value here. So since 3p has a lower n value, so it will be in the lower energy state. So this is the increasing order of energy from top to bottom. Is this clear? So it's very important to understand this. That in how you will decide the n plus n value, and in the case n plus L value is same, you will look at the n value only. Anyone has any doubt in this part? So in this way, you will decide the energy of the given orbital. So that order which you are seeing for the multi-electron system, that was coming from this way of determining the energy. Remember students, that n plus L value is not true for the hydrogen-like species. We have already seen how does a hydrogen-like species behave. So remember that part. Do not apply this to the hydrogen-like species. It is only applied to the multi-electron system. So it's very simple to find the value of L. So for the s orbital it is 0, for p orbital it is 1, for s orbital again 0, for d it is 2. Okay. So I have told you it is not applicable to multi-electron system because the multi-electron system has a second type of force, which is repulsive force. Now we'll try to understand it in a much more detailed way, that how this energy difference is coming. So this is purely due to the involvement of one electron. So L value will be always smaller than N. Yes, it's true. So L value will be always smaller than N, because the value of L goes from 0 to N minus 1. So if the value of L is 5, then the value of N is 5, then the L value will be 0, 1, 2, 3, 4. All these values are less than 5. Okay. Now, let us try to understand why is this energy difference coming, and why there is a disparity from the hydrogen-like species for the case of multi-electron system. So this part is very crucial to understand. Just listen it carefully. So first of all, we know that if you calculate the force of attraction for an electron, then how do you look at it? You look at it from the perspective that it is being attracted by the proton. Okay. So I have written it that the electron which is experiencing a force, it is due to the proton. Now what is the count of proton? It is Z. So what will be the total charge? Z into E. Very simple. So if E is the charge on one proton and Z is the number of proton, therefore total positive charge will be Ze. So this much charge is attracting your electron. So this is the ideal case. But this thing is not happening in actual. Okay. This is true for hydrogen-like species, but in case of multi-electron species where we have more than one electron, the case changes. So you can think of it in a way. Suppose you are standing on a floor, okay, and now someone is throwing water at you, okay, or take a case of light. So you know what is translucent object, which allows only partial passing of the light. So if you are looking at a bulb directly, then it will glow more. Now keep a paper ahead of you. Now you will see that, and if you try to look through the paper, you will experience less brightness of the light, isn't it? Did you get the point? So suppose you are looking at a bulb, you are observing some brightness. In the second case, you take a paper and look at the bulb through the paper. So of course you will see the bulb is shining, but that image will be first of all blur, and second thing, the brightness will be dimmed in this case. Okay. Now consider the same case for the electron. If there is only one electron and one proton, then they are attracting each other. If a second electron comes into play, then that blocks or intervene between the previous between the outer electron and the proton. So what is happening? Your electron which is present in the inside shell, that is shielding the electron present in the outside shell, and due to that it is experiencing a force which is less than the actual force Ze, and in that case we take Z effective, which is the actual force. Is this point clear to all of you? Any doubt in this? So I guess this is simple to understand, that what is this effective nuclear charge. So it is basically the charge that is experienced by electron due to intervention of a second electron in between. Okay. So for Hindi lecture, you can go and visit our website. You will have the Hindi lecture of the same slides in that website. So please refer to that. Now, this shielding effect is different for different electrons in different orbital. What is the meaning of this? So suppose the electron which is shielding your outermost electron is present in the s orbital. So in that case, you would say that the s orbital will show the maximum shielding effect. Okay, so remember it, that the electron that is present in the s orbital, that will have the maximum shielding effect. Then comes your p orbital, and then comes your d, and lastly comes your f. So remember this, that shielding effect is more prominent in the case of s. So if your electron is from the s orbital, it will help in more shielding. Then comes the P, then comes the D, and then comes the F. Now, what is the reason behind it? So basically, the s orbital is spherical in shape. We know it very well. Okay. Now, as a result, due to this symmetrical nature, it is shielding the outer electron more efficiently. Right? Again, I am repeating it. Since your s orbital is symmetrical and it is surrounding your nucleus from each and every side, therefore, as a result, it is having the maximum shielding effect. Now, as you move to the p orbital, you see that there is a nodal plane in the p orbital. We have seen it in the previous class. Now, due to this, it is not surrounding the nucleus in a better way like the s electron was or the s orbital was doing. Similarly, the D is a weaker one in shielding as compared to p, and lastly is your f orbital. So, this order is very, very important for you. So, as a result of this, since your p orbital is poor in shielding as compared to d orbital, so it will be having the minimum shielding effect out of s, p and d. And lastly comes your f orbital. Any doubt in this part? I guess this part is clear to all of you. This shielding effect of different electrons in different orbital. Anyone who has a doubt in this part? Now moving on to the next thing. So next is your penetration power. So two things are there. One is shielding effect and one is the penetration power. So basically, you can think of penetration power as the ability of the electron to go much deeper towards the nucleus. Again, the s orbital, due to its symmetrical shape, it is more closer to the nucleus as compared to any other orbital. So therefore, the electrons which are present inside this orbital, they will have the maximum penetration power or maximum accessibility towards the nucleus. Then comes your P, then comes your D, and lastly your F. As I have told you, so basically this penetration power of s orbital is due to the spherical shape as compared to the p orbital, and as a result of this, your s orbital electrons are spending more time closer to the nucleus as compared to the p orbital electrons. And similarly, your p orbital electrons are spending more time towards the nucleus as compared to d orbital electron, and hence we are getting the penetration power order as s, p, d and f. Now, last thing, we have seen it that for the case of s orbital, if you take the same shell, if you are considering the same shell, you can see it very clearly that the s orbital was having the least energy. Okay. For example, if you were comparing the 3s, 3p and 3d, you were seeing it very clearly that the 3s was having the minimum energy, then was the energy of 3p, then was of 3d. So why is the 3s is having the minimum energy? What is the reason behind it? So it's important to understand. Now, the point is that since your s orbital electrons are spherical in shape and they are close to the nucleus as compared to any other orbital, as a result of that, due to this closeness, the electrostatic force of attraction is high. Now, if the attractive force for s orbital is high, it means its energy is lower. Therefore, for the same shell, the 3s, if you take the third shell, the 3s has the lowest energy, then comes your 3p, then comes your 3d, 3f and so on. Okay. So if you have a doubt, you can write it in the chat section. It is open for all of you. So I guess this point is clear to you, all of you, that why is the penetration power order going like this and why we are getting a different type of energy order in case of multi-electron system. So basically, if you want to understand penetrating power, you can understand in a way. Suppose you are taking a spear which is sharpened, right? So, and in the second case, you are taking a blunt knife. If you take a foam and stab that spear against the foam, the spear will get much deeper as compared to the blunt knife. So that is something which is related to the penetration power. Okay, as simple as that. Now imagine you have three orbitals, S, P and D. So since your S is symmetrical means it is spherical in shape. P is also symmetrical, but not as much symmetrical as your S orbital. As a result of this, it will come closer to the nucleus. It means it will penetrate more. Of course, your electron will not go into the nucleus, but it will come closer and closer to the nucleus. As a result of that, the S will have the greatest penetration power, then comes your P, and then comes your D, and lastly your F. Next thing I was making a strong point here is that since your S orbital is penetrated or more closer toward the nucleus, therefore it will have a higher force of attraction, okay, due to the less energy between the nucleus and the S orbital, and therefore since the force of attraction is increasing, therefore its energy will decrease because attractive force increase will decrease the energy. I guess it is clear now. Now moving on to the next thing. So what we can say that the energy of S orbital will be lower than the energy of P orbital. We have seen this. Then the energy of P orbital will be lower than the D orbital. And due to this difference in energy, we are seeing the splitting of the energy level. So basically the 3s, 3p and 3d should have the same energy, but because of the greater penetrating power of the S orbital, the energy of the S orbital is going down, and as a result, the 3s orbital or the S orbital has having the lowest energy. Then comes your 3p, 3d. Now this is called as splitting of energy. 3s, 3p and 3d were having same energy initially. Now they are splitted. First is the lowest in the lowest is for the 3s, then a higher one is the 3p, and lastly is your 3d. I guess this point is clear to all of you. So what we can say from here, that due to the different penetrating power and a multi-electron system and a repulsive force between different electron, the energy between the orbitals for the same shell is changing. So why is S having a lower energy? So I'm trying to explain that thing again and again. So let us try to understand it. You have your nucleus. I said it. Suppose this is your 3s orbital. Okay. Then this is your 3p, larger in size. Okay. And lastly, you have a d orbital. So suppose we are comparing S and P. Since your p orbital has a lower penetrating power, it has a lower penetrating power. That means it is far away from the nucleus as compared to the S orbital. So we can say that for p orbital, the distance between your nucleus and negative charge is high. Okay, so R is high. So you know that force of attraction is inversely proportional to the distance square. Since your distance is increasing for the p orbital, therefore its force of attraction is decreasing. Now, if the force of attraction is decreasing, and force of attraction is simply what? It is an attracting force. Okay. So you are saying that your attracting forces are decreasing. Now this is a very important point to remember for all of you, that if your attracting power or the attracting forces decrease in any way, that leads to increase in the energy always. Similarly, if your repulsive forces, okay, if your repulsive forces are decreasing, that would result to decrease in energy. Is it clear? Anyone has a doubt from now in this point? Okay. Now let us move to the filling of electron. We will try to understand each of these principles one by one. So first is your Pauli exclusion principle. So it says that no two electrons in an atom can have the same set of 4 quantum numbers. So this is the point that was made by Pauli. Now what is the meaning of this? Let us try to understand this point. Okay, before that, the result of it was that no two electrons can have the same spin if they are present in the same orbital. And second thing is that no orbital can have electron greater than 2. Okay, so two things are there, that no two electrons can have the same spin if they are present in the same orbital, and more than 2 electrons are not allowed in a given single orbital. So if I try to illustrate it with the help of an example, let us take a case that suppose your 1s orbital is having 3 electrons. Okay, your 1s orbital is having 3 electrons. So what will be the quantum number for each of this? So I have told you that according to Pauli exclusion principle, no two electrons can have all 4 quantum numbers same. Okay, no two electrons can have all 4 set of quantum numbers same. So for the first electron, if we take, then what can be the possibility of the principal quantum number? It will be 1 because it is present in 1s. Then the value of L is 0. Value of Ml is again 0 because for the s orbital, only one value of Ml is possible. Now, suppose we take that, of course, your electron is present in the plus half. Okay, so this is the first thing. For the second electron, we have taken all 3 values same because again we are taking it for the 1s orbital only. But in this case, we take it as minus half. Why we are doing it so? Because we want to keep this Pauli exclusion principle true. Now you can see for these 2 electrons that they have 3 same principal quantum number, but the fourth one is different. Okay, so these 2 electrons are not violating the Pauli exclusion principle. Now what we do? We try to insert the third electron in that same orbital. Again, the third electron will also have the same value of all of this. But now we are confused that what value should we keep for the spin. Okay. So we are taking 3 electrons in the same orbital. We can't keep it anything. No, it will be not plus half. If you keep 3 electrons in the same orbital, so that will result in a case where these 2 will have the same set of all 4 quantum numbers. Okay. So therefore for this reason, you can't put a third electron in the same orbital, which is ns. So one orbital can have maximum of 2 electrons. Any doubt in this? So I guess this part is clear. So basically what it is trying to say, that if you are taking an electron and you are comparing it with the second electron, then it will not have all 4 quantum numbers same. No, this question mark will not be equals to plus half. So basically what I am trying to say is that you can't keep a third electron in the same orbital, because if you keep it so, then you can't keep the value of ms. If you take it as plus half, then 1 and 3 electron will be identical, which is false from the Pauli point of view. If you take minus half, then second and third will be the same. So again it is violating the Pauli exclusion principle. So we can say that putting third electron in the same orbital violates the Pauli exclusion principle. Now moving on to the next rule, which is Hund's rule of maximum multiplicity. What does it say? So it says that suppose you are filling up a orbital, okay, Now, you're filling up a orbital in a subshell. In filling up that, you can't pair up the electron until and unless all orbitals are filled singly in a given subshell. Okay. Suppose you take the case of P or P subshell. So P subshell has 3 p orbital, px, py and pz. Okay, 3 orbitals are possible for the P subshell. So you will put the first electron in the px, then you will put the next electron in the py and last in the pz. Then after that you will start pairing each of them. Before that you can't pair it up. So suppose if you take the case of P, D and F, you will only start the pairing when your p orbital is having each orbital filled with 1 electron, that means 3. Similarly for D, each orbital is filled with 1 electron, which is 5, and for F it is 7. So pairing of electron will take place when we are putting the 4th electron in the case of P, the 6th electron in the case of D, and 8th electron in the case of F. Now remember a very important point, that your half filled and full filled or degenerate set of orbital, they have more stability always, and that is happening due to the symmetry. Okay, so due to symmetry, the half filled and full filled will always have a higher energy as compared to the other orbitals. So we'll see the reason behind it. Okay, if you talk about the above principle, so basically it is seen that if you are filling up the electron, then the ground state of the atom will have the electron first filled. Okay, so we have already seen that how do we distribute the energy. So we know it very well that the 1s had the lowest energy, then your 2s, then 2p, then 3s, okay, 3p, 4s and so on. So remember this part always, that if you are filling up the electron, then first fill the electron in the lowest orbital or the lowest subshell. So 1s has the lowest energy, so fill it first, then fill the 2s, then fill the 2p, then the 3s, 3p. Okay, so this is a very simple but important point to note. Okay, I guess this principle has a very small aspect and easy to understand. Okay, because already we have decided the energy for each of the subshell with the help of n plus L value. So the one with a lower energy will be filled first, and then we will fill the upcoming one with a higher energy. So it is very simple to define the electronic configuration. It is simply the distribution of electron into orbital of an atom. So the configuration is what? If you take the word configuration itself, it is basically defining a structure. So you are trying to distribute the electrons according to the shell. Now it can be represented in two ways, very simple one to understand. First is that we can write it in this way. So if it is S, just put a number here. So we have taken it as A, B, C. You can take numbers instead of this. The second way is the use of orbital diagram. So you take orbitals in the shape of this cube and fill electrons in these cubes. Now let us take an example of elements to understand this part. Suppose if we are taking the sp denotation, then for the case of hydrogen, the electronic configuration would look like this: 1s1. For the case of helium, it will be 1s2. For boron, it will be 1s2, 2s2, 2p1. Okay. And then for carbon, it will be 1s2, 2s2, 2p2. So basically, we are filling electrons and we are filling it in the form of increasing energy, where we are deciding the energy with the help of n plus L value. So it is the electronic configuration. Next we have nitrogen. So nitrogen will have 1s2, 2s2 and 2p3. Then we have oxygen. So we are filling the electron in the P right now. Then comes your fluorine, and lastly your neon. So in this way, you will show the notation for the different electronic configuration. Now let us look for the second type of notation, which is your orbital diagram. So in this you will understand that what each principle is saying. Okay. So first let us take the case of hydrogen. So hydrogen has an atomic number of 1. That means it has 1 electron. So let us fill it here. Very well. Now take the case of helium. It has 2 electrons. So both will be present in the 1s2, which is this. Now why we are filling the 1s first? Because it has the least energy. The n plus L value for 1s is 1. Okay, so we will fill it first according to the above principle. Now, yes, you can use both of the methods. Both are true, but try to use the SPDF notation. That one is much easy to use and it is more used in the books also. Now moving on to the lithium. Now there is a third electron for it. So we fill the first electron here, second here. Remember, keep the spin opposite, or if we don't do it, then the Pauli exclusion principle will be violated. Now, for the case of lithium, can we keep this electron here? No, it's not possible. We have seen that an orbital can not have greater than 2 electrons. So we keep it in the 2s. Why we are keeping it in the 2s? Because after 1s, 2s has the lowest energy. Yes, there are questions from the electronic configuration from this part always. Then coming on to beryllium, which has 1 more electron. So we put it here. Now we have filled the 1s and 2s up till beryllium. What about boron? So for the case of boron, we will now move on to the 2p, because 2s and 1s are already completely filled. In this way, you will go on filling the atomic orbital and you will get the orbital diagram. Now I have told you in the Hund's rule of maximum multiplicity that the half filled and the full filled orbital are more stable than other orbital. How we are saying that? Why it is so that the stability of the half filled and full filled is more? So let us try to understand that. So basically, when we are taking any symmetrical thing, in nature it is seen that symmetrical things are more stable as compared to unsymmetrical things, right? So if we are taking a half filled or a full filled case, then the orbital looks symmetrical. Okay. Now due to this symmetry, we are gaining some stability. What is the second thing? Second thing is that the exchange energy, right? So let us try to understand that thing. So basically it is seen that due to the presence of half filled and full filled orbital, there is a chance of exchange of the electron between two orbitals, which releases energy, and as a result of that, the system becomes more and more stable. So this can be understood with the help of this diagram. So if you look at this diagram, so this is basically indicating a d orbital which is having 5 electrons, right? So we have filled half in each of them. Now you can look at it, it is very symmetrical. Okay, you can just draw a line in between and you will get same thing on the either part. If it was having more than 5 electrons, suppose 6 electron, then it would not look symmetrical. As a result of this, it is more stable. So this is the first reason I have mentioned. What is the second reason? Second reason is the exchange. Now since this and this are having the same energy, because they both are in the 4D or 4D subshell. As a result of this, they both can exchange their position. Okay. Now, since they can exchange their position, that leads to delocalization of this electron, means they can move from one part to another. Now, whenever there is a delocalization of charges, because electron is the charge, there is a decrease in energy. Okay, and due to this delocalization or exchange, we see that the half filled and the full filled are more stable. Thank you.